Good afternoon, everybody. This is the first live session for the course Nuclear and Particle Physics on the MOOC's NPTSM platform this year. Basically, the live sessions are introduced so that the students will have an opportunity to interact directly with the lecturers, as the course is otherwise online. So unfortunately, we don't have a direct interaction on face to like on the. It's possible through the live chat only. Therefore, all of you are encouraged to actually write down if you have any queries or questions regarding the course so far or anything related to that, or in whatever I'm going to kind of speak today. Okay, I will try to address those queries as well. Okay, so in essence, the course is about understanding the constituents of matter that we have. We have many things around us, many different objects, but then it's believed that we can go on a kind of deductive way of understanding things by considering some small building blocks of this. Particles. By the way, I think I don't see the screen on the channel. So is there anything that we had to do from our technical side, or is everything okay? Okay, while the technical team is going to sort that out, let's continue with our studies. So I did share the screen. Okay, I'll try again. Share. Bring it down. It still is not sharing. Okay, I'm sharing the screen now, no problem. All right. Okay, sorry for that interruption. Basically, today we will kind of first few, maybe 10 minutes or 15 minutes, I will take up a few things which usually some of you have mentioned as not very clear in the course so far. Okay, and one of the things that came to our notice is this angular momentum addition. Perhaps this is a new concept, or it's not really elaborated in the course lectures sufficiently enough for all of you to understand, perhaps. Okay, so let me spend a few minutes on that. Angular momentum, including the spin of the particle, is an important property of any quantum system. including the nucleus or elementary particles like electrons, etc. So now in various different processes, what happens is that the energy is transferred. Say, for example, when there is something decays to some two particles, then the energy of the initial particle is shared between the final particles. This could include photon emission in terms of the energy emitted in terms of radiation as well. Along with the energy, there are other properties which are also to be considered in such processes, which is, say, for example, a nucleus is beta decaying or alpha decay of a particle nucleus. Or when we consider the elementary particles, the decay of an elementary particle later. Or it could also be the scattering between different particles, any interactions. Such interactions will also require consideration of angular momentum. Angular momentum in quantum mechanics is a vector quantity, but it is not exactly like a classical vector. In the sense that if you have two systems with spin 1 and say I1 and spin I2, or angular momentum I1 and I2, when we consider the combined system, the combined system can have angular momentum in a discrete manner. I mean, different possibilities of total angular momentum of the combined system can be actually thought about as integer, a discrete set of values ranging from the difference between these individual angular momenta, that is I1 minus I2, depending on whether I1 is greater than I2 or I2 is greater than I1, we can take the difference, keeping the bigger or the larger angular momentum taken first and subtracting the smaller one. And an easy way to denote that is to take the modulus. Whether it is negative or positive, it will give you a positive number, because this angular momentum is a positive quantity. It's a length kind of thing. That is the minimum possible angular momentum of the combined system. Then you can have this plus 1 or plus 2, etc., or up to I1 plus I2. Okay, so you can actually have, in the case of, say, an example, I1 equal to 1, I2 equal to 2, you can have it from value 1, which is the difference between I2 and I1, and up to I1 plus I2, which is equal to 3. 2 plus 1 is equal to 3. So all values between 1 and 3, differing by a unit of 1, are allowed. By the way, we are talking about angular momentum in natural units. When I say natural units, the Planck constant h bar is taken to be equal to 1. Otherwise, all these have to be multiplied by an h bar, which was the correct unit of the angular momentum. Okay, so this is basically the rule for angular momentum addition. Whenever you combine two angular momenta, or whenever you think about a system which is made of constituents having the angular momenta, we can consider this rule. This is what we have to consider. Say, for example, in our specific case where we have been discussing nuclear physics, the alpha decay of nucleus. Let us consider a nucleus X decaying to nucleus Y and an alpha particle. Now, in the initial stage, there is only one particle. Of course, it's a composite particle, but we consider it as a one unit, the nucleus X. And in the final stage, we have a nucleus Y, that's one unit, and an alpha particle, two different parts of the system. This Therefore, initially we have one angular momentum for one particular nucleus X. It is the spin of the parent nucleus. And finally, we have the daughter nucleus Y, its spin, and the alpha particle. And there could also be some orbital angular momentum between these two particles, which we denote by L, small l here. So Iy, I alpha, and small l are the angular momentum components. The components in the sense that different parts of the system having this angular momentum. Initially, you have only one thing. There is only the nucleus and its spin, which we denote by Ix. There is no orbital angular momentum because there is only one particle, and then we can always go to the rest frame of that particle. With respect to some other origin, this can have an angular momentum. But for simplicity, we will go to the rest frame of this particle. That will not give any of the results wrong when we actually consider a system where the origin is different from the position of the particle, or the if the reference frame that we are considering is different from the rest frame of the particle. Because the same addition will happen in the final state also, because we have to use the same reference frame for both sides. So that is not going to, it may complicate the calculation a little bit, but it is not going to give you anything in any additional information. So it is, for simplicity, we go to the rest frame of the particle. And in that, Ix is the only spin or angular momentum that we have in the beginning. Then we have Iy, I alpha, and L in the final state. Among these, I alpha is experimentally found to be 0. So that means that's an empirical fact. So this can be neglected. So then we have only two of these, Iy and Il, and we know the angular momentum addition rule. Therefore, Ix should be one of the possible values allowed according to angular momentum addition when Iy and L are combined. Okay, so what are the values that are allowed here? Is Ix is equal to Iy minus L, that is the minimum, Iy minus L, the modulus, plus 1, plus 2, up to Iy plus L. All of these are positive quantities. Okay. So let's take this example of Ix equal to 2 and Iy is equal to 3. And the decay is X going to Y plus alpha. So as we said, the possible values of Ix, we'll assign the value of 2, but let's take, we don't know here what is L value. So our attempt is to find out what are the possible L values. But we will turn it around, because in the final state we have these two particles. So we have to actually combine those and then see what are the possibilities of L. That will give you Ix equal to 2. That's what we do. So L equal to 0 if you consider Iy minus L is equal to 3, Iy plus L equal to 3. There is only one value which is allowed when Iy equal to 3 is combined with L equal to 0. But that's not equal to 2. On the other hand, we are given that Ix equal to 2. That's given, or that is experimentally measured, say, in this example. So this cannot be a possibility. So we can rule out L equal to 0 as a possibility in this case. How about L equal to 1? In L equal to 1 case, we can actually take Iy minus L, that is equal to 2, and Iy plus L, which is equal to 4. So certainly the X can be anything between 2 and 4 or 2, 3 and 4. So it is possible to have Ix equal to 2. Turning it around, for Ix equal to 2 and Iy equal to 3, orbital angular momentum can be 1. Is that the only possibility? Let's go ahead and see. L equal to 2. Yes, L equal to 2 will give Iy minus L is equal to 1. And Iy plus L is equal to 5. So between 1 and 5, certainly there is 2. Therefore, X equal to 2 is allowed. Similarly, you can see that all other values are allowed. So L equal to 1, 2, 3, 4, 5, etc. are possible values of L in the case of Ix equal to 2 and Iy equal to 3. Usually, the lowest one is preferred in an interaction. That's because when we actually compute the probability for this thing, this decay, then that the lowest value will have much higher probability compared to the higher ones. So in this case, it could be 1. But there is also one more consideration, which will actually need to be taken into account. That is parity. What is parity? Parity essentially is saying that if we are considering any system with all coordinates taken to be x, y, and z, then if somebody else is considering a different system with compared to this x, y, z, his coordinate system corresponds to minus x, minus y, minus z. Which means that you have a system, you have a reference system where you have actually inverted all the coordinates or all the reference axes. Now, usually in physics, in most of the physical systems, parity is conserved in the sense that if it is one way, it is some physical property, some physical reaction or process happens in studied in the XYZ reference frame. And if somebody actually studies the same system with rules, with same physical rules in minus x, minus y, and minus z reference system, then we can say that we expect exact same result. There's a symmetry between these two systems. This is called the parity symmetry. So we will say that parity is something which has to be conserved, which should not be changed, which should not be different in that. And in quantum mechanics, wherever we have a system with an angular momentum, the corresponding system, because of this orbital angular momentum, the parity of the system can be taken to be minus 1 power L. This is something which is difficult to explain today here. I would urge all of you, if you don't know, to look up elementary quantum mechanics textbook or look at any of the course on basic fundamental quantum mechanics, which was a prerequisite for this course. So we are not getting into a discussion on that part here. But if anybody has any specific question on this, please write to me. I'll be able to direct you to the right place to look for this. Okay, so which means that if you have a system with orbital angular momentum L equal to 1, then minus 1 power 1 is equal to minus 1. And if it is having an angular momentum 2, then it is minus 1 power 2, which is equal to plus 1. Parity can only be plus or minus 1. That's why it is minus 1 power L. Whatever the number that you have as orbital angular momentum, it is always an integer value. As I said, we are working with natural units. So h bar is not or is considered as 1. In this L here is the angular momentum in units of h bar. So we can only have an odd or even parity possibility. That is how it is. So there are only two possibilities, +1 or -1, depending on whether it is odd or even or odd respectively. So in the previous example, we could take L equal to 1, 2, 3, 4, 5, okay, etc. But now we need to also know what are the parity of these nuclei, which means that this is also experimentally measurable. And we had talked about it. This is there in so you can actually consider this angular momentum and parity. Okay. So X, let us say, has a parity plus, and Y also has a parity plus, which means if you take the corresponding wave function in quantum mechanics corresponding to this nucleus X, then that corresponds to a function with positive parity. In a sense, it is an even function of the coordinates. I mean, in a vague sense, but basically, we have to remember that we are working with 3 dimensions. And let us say Y, the nucleus, the daughter nucleus Y also has positive parity. Then the change in the angular momentum is the important thing here when we consider the relative angular momentum. So the relative angular momentum in the final ray is basically only should be even because there is no change in the parity to get absorbed in that L part, orbital angular momentum part. Similarly, if it is -1 and -1 odd parity, parent particle decaying to an odd parity daughter particle, then also there is no change in the angular momentum and therefore, change in the parity. Therefore, the angular momentum has to be even. Then only you will get +1 with that. Okay, there is no change. If there is a change, on the other hand, plus to minus or minus to plus, then L is an odd number. So depending on this, the lowest value of the angular momentum can be either 1 or 2. This is the kind of thing that we should consider, and we have discussed this in the course, but I just wanted to elaborate it in case some of you have difficulties, as some of you have indicated. Now this, and for the examination and for your future studies also, this is going to be important. Okay, so the rest of the 40 minutes or less than 40 minutes, we will actually discuss something which is slightly outside the course, but which is very intimately connected with the course. We have now entered the elementary particle discussion in the course, okay? And you are somewhat already familiar with what is the elementary particle from the course. And I will give you some kind of motivation for studying that and then give certain properties of that, which we could not cover entirely in the course. Some of these have good overlap, but I mean, there are things which we could not discuss in the course as well. This is something which we said, like everything around us, terrestrial or non-terrestrial, stars, all the heavenly bodies, Earth, all things on Earth, our solar system, and everything are made of certain number of elementary particles. We have been trying to understand the system in the physics. What we do? We want to understand what are the things that we have around us and how are they working. The physics will not get into the life and how consciousness or life is originated, etc. We kind of want to know the dynamics of things otherwise. For example, what is solar system, and then how Earth moves around sun. What do you mean by all these celestial bodies? Or on terrestrial, these things, how things work. Okay. For example, how a car works. Basic underlying principle are all understood by the physics of it. Similarly, any complex system also, the study of that comes under physics. So that is how we see. Especially in particle physics, what we are focusing on is what are the constituents, the basic constituents of everything. We knew quite a lot already before coming to the present kind of understanding. Atoms, concept of atom was already there for centuries now. And later we saw that there are constituents for this atom also. And we have discussed some of these ideas in the course. So basically, at the moment, we understand that all matter around us are made of molecules with then atoms. Atoms have nucleus, which is basically the first part of the study that we have in this course. And then the nucleus has constituents called protons and neutrons are further made of what are called quarks. And then there are also electrons in the atom, which are basically elementary particles. Okay. So the scale at which that we know, we kind of explore our physics now, or in elementary particle and dynamics is now to the length scales of 10 power minus 18 meter, so atometer. Now, this means that we need to have a very, very, very powerful microscope, in a sense, to see these things, which is what is provided by the elementary particle collision experiments, like the Large Hadron Collider, if you have heard of it. On the other hand, then there's this nucleus, the forces. We have the nuclear strong force, the weak force. Okay, we had discussed this in detail in the course, right? I am sure you are all familiar with it now. Okay, so in beta decay, for strong nuclear force is the one which holds the nucleus together against the repulsive electromagnetic force, whereas weak nuclear force is the one which causes it to decay, like in the beta decay, converting a neutron to a proton and an electron and what's called the neutrino, which is a tiny mass, almost massless, but with this very, very small mass particle. Okay. And then there were these kinds of study we wanted to do, understand what are the basic interactions of basic other dynamics that can be there, or whether there are things that comes from Earth, outside the Earth, etc. So there were these cosmic ray experiments, balloon experiments that happened in the early part of the 20th century, last century. And it's basically some charged devices. I mean, the devices which will detect the charged particles, etc., which are sent to the upper atmosphere Oh, is that okay now? Okay, somehow it went to the other. I don't know how. Okay, sorry about that. So let me repeat what I was telling. So basically, at the moment, we have electrons, muons, and tau leptons as the elementary particles similar to the uh, electrons. They are all called leptons, and they are very light compared to other particles like the proton, etc., or even some of the quarks. Quarks are the ones that make the hadrons like protons, neutrons, etc. And we have up type quark, down type quark, charm quark, strange quark, top quark, and bottom quark. Now these quarks are all discovered. All these leptons are also discovered. And we can actually see, I have listed here the different the different experiments, in a sense, the different experiments which have actually discovered some of these elementary particles. And in fact, many of these have actually been shared Nobel Prize for their discovery also. So at the moment, this is the picture that we have. My idea is not to get into the detailed discussion of this discovery or the model itself, but to just give you a flavor of what's going on. So let me don't digress, but let's say that this is the picture that we have as far as elementary particles are concerned. And some of all the quarks that we have a property, strange property, in a sense that we cannot see them freely like electrons. Electrons from the atom can be ejected. I mean, you can actually make them free and then they can move freely. Whereas quarks, you cannot actually take out as a free quark. There are certain properties associated with the strong interaction that actually make them slaves of these dynamic and then make them always go in a combination of other quarks or anti-quarks. So that we can have protons, which is a combination of three quarks. Proton can be free and move as a free particle. Neutron can move as a free particle, but it is a combination of three quarks. Pion is a combination of a quark and an anti-quark, and you can see free pions, but you cannot see a U quark or a T quark, or a D quark or things like that moving freely. Top quark is a little bit of an exception. It's not an exception to actually it behaves differently compared to the other quarks. It's because of a different reason. The reason is that it is very, very heavy, and it so happens that such a heavy particle will decay very fast, and it is not very stable. If you produce a top quark, before the time that it gets to actually combine with other quarks around it in an environment, in fact, quarks, if you produce a U quark, it will pick up a quark from vacuum also, and then combine it with. In fact, you cannot produce a quark alone. You have to always produce them as particle-antiparticle pairs. So if you produce a top quark and anti-top quark, they, before combining, before getting time for them to combine, or before getting time for them to pick up other quarks and then form a kind of a bound states, combined state, they decay. So the decay time is so small for top quark that it is going to decay before it actually combines. So we do not have any baryons like proton with top quark as a constituent. We have mesons and baryons with even B quark as constituents, strange quark, charm quark, D quark, I mean up quark, all of this. But top quark, no. So top quark decays in. You see, that is the only exception here. Apart from that, all quarks are the combined states of all the quarks are seen. And then we have experimented with it. We have studied this. And top quark also decays, and a lot of studies are done on that part. And top quark is the latest of the thing that we have discussed in the quarks that we have discussed in the elementary particles in 1995. And then the Higgs boson, for some reason, it exists. Essentially, that is the one that actually is the reason. The interaction of all the elementary particles with the Higgs boson is what gives the mass to these particles. So this was the idea that was proposed long before, and then finally we could discover such a Higgs boson about slightly more than 10 years from now. Okay, so that is basically the idea that we have here for these elementary particles for the time being. Okay, and now all those particles are there. Many different elementary particles we said, like charm quark, strange quark, muon, tau lepton, top quark, quantum quark. It so happens that they are kind of a heavy copies of these electrons, down type quarks and up type quarks, etc. And they are very unstable. So the stable things are formed with electron and down and up quarks, like the proton, which is one of the stable particles in nature. That is why atoms exist, and then we all exist. Electron is a stable particle. That's why the atoms exist. Again, we all exist. And the top quark, the protons and neutrons are made of up quark and down quark. Two down quark and an up quark makes a neutron. One down quark and two up quark make a proton. An electron moves around it in the atom. So that is how everything is made of. So it is in a way amazing to see that everything that we see on Earth, the Earth itself, all other celestial bodies, everything that we see in this universe are made of these three elementary particles. Other heavier elementary particles can be just produced and decay. They may be produced in an environment, in the laboratory, in a celestial environment, like interior of some star or somewhere. But they don't exist there forever or for a long time. They just decay. The one that exists, that can actually survive, that survive for a long time, that 8.5 billion years of the age of the universe, is or are the combined states of these three particles, three elementary particles. That's something which is truly amazing in my opinion. Okay, so the elementary particle study is all about understanding everything, all the dynamics of all these particles, the particles themselves, and then understanding their dynamics in detail. So rest of the course, we are going to discuss some of these properties. I mean, the field has actually gone into different diverse directions and in-depth analysis and study. Therefore, we can only introduce the topic, introduce the dynamics of the elementary particles in this course. And quite a lot of things are there beyond what we can cover in this course. So let me continue. The other thing is the dynamics of this itself. So for example, you know a lot of things like atoms have radiation. Atoms can be excited, and excited atoms get de-excited by radiation. And that is how we see light. Anywhere, everywhere, we see light by, well, not everywhere. LED is a completely different mechanism. It's a kind of a different mechanism. But in the sun, for example, we have light emitted by all these different particle processes. In fact, even in the LED or any other this thing also, it's all elementary. The particle, excited particle going into giving away energy. That is a kind of thing that happens. So it's basically the electron in a higher energy state comes down to a lower energy state, emitting the particular quantum of energy or difference in the energy in a quantum, in a short, and that short is basically the photon corresponding to that energy. And a collection of such photons is basically the radiation in general, electromagnetic radiation in general, and light in particular, which we know very well now. Okay, and we also know that the atoms can combine to form molecules, and all of chemistry will deal with that. That's basically the atomic physics and chemistry and other these things. And when you come to the elementary, the subatomic particles, the nucleus decays, as we discussed a little bit, the alpha decay. Yeah, okay. So the alpha decay happens, and that's because of the beta decay. So the alpha decay happens, then the beta decay happens, and all these things are because of other dynamics. And one of these things is basically called the weak interaction. So the weak interaction is different from radiation that we consider from atoms. So there are other dynamics when we come to elementary particles at the subatomic level. At the atomic level, it's basically the electromagnetic interaction, the Coulomb interaction between the nucleus and the electron, and other interactions, not just the Coulomb interaction, the spin interactions, etc., also come into play. But basically, it is the electromagnetic interaction. Whereas the subnuclear level, it's not the electromagnetic interaction. It is mostly the nuclear interactions which are to be considered. So beta decay is kind of understood by what's known as weak interaction, which is fundamentally different from electromagnetic interaction. Okay. There are rules also here. So relevant to our course here, I would say spend one slide. And in this, say for example, when we consider the neutron going to proton and electron, we do not have a process where n going to p plus e minus l1. This was the moment of discovery of the neutrino. Beta decay, although electrons are seen, nothing, and protons, of course, can be figured out from the parent nucleus and the daughter nucleus. There was no other thing. And then it so happens that the energy spectrum of the electron measured, if it's not matching with what is expected in a one particle going to two particle decay. So it was postulated to have a particle which is kind of not seen, but is emitted, taking away energy in the form of its kinetic energy. And that particle was named neutrinos. Now that is okay. That's then in the theoretical understanding finally, when we consider the theoretical, there are various considerations. One of those is the symmetry consideration. So there are various different conserved properties. One of the conserved properties is called the baryon number. Other is called a lepton number. All the hadrons like neutron, proton, and all the quarks, or anything that is made of quark, are called baryons or mesons. Mesons are, so if it is only the quarks, okay, then it is a baryon. If it is equal number of quark and anti-quark, because anti-quark has opposite baryon number, they cancel each other. So it is its baryon number is 0. So they are called, such combined states are called mesons, like pion. Pion is a meson, neutron is a baryon, proton is a baryon. Neutron has a baryon number 1, proton has a baryon number 1, pion has baryon number 0. And electron has a lepton number 1, proton baryon number 0, neutrino has a baryon number 0, lepton number 1. What is produced here is an antineutrino, and that has a lepton number -1. So in this particular thing, whenever the second line, n going to p plus e minus nu bar, one baryon with lepton number equal to 0 and baryon number equal to 1 is decaying to another baryon p, which has a baryon number 1, lepton number 0, electron with a lepton number 1, baryon number 0, antineutrino, which has a lepton number 1, antineutrino, which has a lepton number -1, baryon number 0, tells you that initially there is one baryon number, finally there is one baryon number, and lepton number is 0 because E minus and nu bar have opposite lepton number, so it's okay. From the same account, you can say that n going to pi plus E minus nu bar is not allowed because the baryon number is not conserved. Lepton number is conserved. E minus and nu bar cancels their lepton numbers each, but we don't have a baryon in the final state. Similarly, for the fourth one, n going to p plus E minus and a neutrino instead of an antineutrino is not allowed because lepton number is not conserved. E minus and nu bar both have lepton number -1. They were +1, so they don't cancel each other. And the last one, we have an antineutrino, but this antineutrino is of a different type. That's also not allowed. Not enough. So it has to be of a special kind. We remember we had actually listed 3 different type of neutrinos: electron type of neutrino, muon type of neutrino, and tau type of neutrino. So what comes in the beta decay is basically the electron type of antineutrino, not muon type of antineutrino, because for each of these individually there is a lepton number. We can denote it as a Le, L mu, L tau. So they have to be conserved separately as well. Again, so I have given one more of this, a little more about details about this, and listed also the family or flavor specific lepton numbers, and also listed some of the processes to illustrate what is allowed and what is not allowed, which quantity is conserved and which quantity is not conserved in different processes given. So I think I would urge you to actually go through these things in a little bit detail. If you have any questions, then you can actually send me a mail and we can discuss that. Okay, you can take a snapshot of this and look at it more carefully, and then see if you have any difficulty in understanding any of these concepts. Please let me know. Okay, so I think I will end soon in another 5 minutes or so. So basically, we are discussing all these elementary particles, and in the course we will be actually restricting to just some of these ideas in elementary particle dynamics. But basically, as I said earlier in the beginning of this discussion, that our motivation was to actually understand things around us, which includes things, celestial things as well, and in fact, how all of the universe, including what's its origin and then where it is going and how is it evolving, etc. So that part is a bit of a slightly different kind of study, including the other concepts, and it's known as the cosmology and in the study of the universe. But the elementary particle dynamics has a big role to play in the early stages of the universe, definitely. And at later stages, of course, we are dealing with a huge universe there. Therefore, as such in the universe, these elementary particle interactions is not relevant in the cosmology, but it is still relevant in the case of smaller systems like stellar evolutions, what's happening inside the stars and different types of stars. And so in a localized way, that is relevant. But what's more interesting, at least more interesting to me, is the role of elementary particles in cosmology in the beginning of the universe itself. So, how everything is created, we now have to understand by saying that in the beginning, maybe there were all small elementary particles. It cannot be imagined like sun was created just in the beginning of itself, and then it is there even now. So the idea of present day cosmology is that all matter, all the structure that we see in the universe was kind of evolved from early stages of the universe where there were no such structures but only some mixture of elementary particles. Okay, and everything evolved from that. And this is a very, very interesting study. And definitely the dynamics of the elementary particles at that time had actually a huge role in playing to play in the evolution of the universe further, right? So that's something which we may actually take up for our discussion in the next live session, maybe. So at the moment, I will stop here and then see if there are some questions that you have specific this thing. Yes, I can see that one. Oh, there was no sound. I guess that was figured out and by the team. And then thank you for informing us. So how will the exam be conducted? Paper and pen or online? It will be an online exam. So it's basically like your assignment thing. Yeah, the rest of the details you'll have to find out from the NPTEL thing, but it will not be a descriptive type. It will be an objective type thing. There will be short answer in the sense that the fill in the blanks kind of a thing. Okay, where similar to the assignments, maybe it is a number, decimal the number with decimal places, or the rest of the details you'll have to find out from the NPTEL thing, but it will. That is it. That is the way the exam would be. So I don't really see many questions otherwise. So all the best, and then enjoy the course, and hope you are all having good time. Okay, one more thing. What is this? So what is the physical meaning of lepton number and baryon number? Okay, so this is like charge in a sense. Okay, in a vague way, we see that not, say for example, Coulomb force. Not every particle is every object experience Coulomb interaction or electromagnetic interaction, electric interaction or magnetic interaction. Only electrically charged particles experience electromagnetic interaction. So that is the way we understand by saying that the electric charge is a property that can be associated with certain elementary particles or other objects, and if some object, including elementary particles, have this property, non-zero electric charge, they will take part in electromagnetic interaction. In a similar way, baryon number and lepton number are properties that we associate with certain objects. So leptons, for example, will not take part in strong interactions. That's why
we don't have nuclei formed with electrons or tau nucleus or something like that. I mean, tau leptons, we don't have any such thing. Whereas protons and neutrons are baryons, and the baryon number associated with them is one of the things that we can consider as property associated with strong particles. Leptons, on the other hand, is something which take part in the weak interactions. But basically, any particle which take part in weak interaction but do not take part in the strong interactions can be called a lepton in a way. Okay, so this is just a categorization to understand what is what. Can you explain electric quadrupole moment? So you know electric dipole moment, right? If you have two charges, the positive and a negative charge, the dynamics, the equations of motion will involve not just the potential like Coulomb potential between them, but there has to be other moments that have to be considered. So it is not just the total charge in a system, but how the charge is distributed. That the dynamics, including the electromagnetic, just considering the electromagnetic interactions will depend not only just on the total charge of the system, but also on the distribution of charge. Say, for example, if you consider a combined system, say a dumbbell kind of a thing with two kind of bulges in it, and each bulge has a concentration of positive charge and a negative charge. But in total, the total charge equal to 0. But they are not distributed such that everywhere it is 0 or not concentric not in a concentric spherical way, but it actually has a distinct distribution, so that the charge centers are separated. In such cases, it's not just the Coulombic interaction of that is important. Also, other type of dynamics is important. So this dipole interaction is one of the things that can be imagined as a simple thing in distribution of charges, other than just the concentric distribution of charges. But quadrupole moment is the next type. You can have the total charge, but take two dumbbells, keep them perpendicular to each other, and two of them have positive charge and two of them have negative charges. That is like a quadrupole. Quadrupole means there are 4 poles, 4 different charge centers for that. So this is arising from that. So in a sense, you can actually think about multiple of this. There is no limit to that. But the point is that in any kind of a charge distribution, the first thing that will come out is if the total charge is not 0, that will be the strongest kind of influence. And then the next one will be the dipole, 2 charge center kind. If it exists, that will have a more stronger influence compared to quadrupole. Then like that, multiples of that you can think about. So that is a way that we can understand. In nuclear physics also, what happens is the nucleus is a combined system of all those things. So the charge distribution need not always be like a uniform spherical distribution. So deviation of the positive and negative charge from the sphericity, that is causing all these different dipole, quadrupole moments. Can you suggest any book for particle physics problems or for nuclear and particle physics course? Yes, I can put it in the chat right away, but I can also voice chat. Okay. All right, I'm not sure if I can do that in the chat. Okay, what I will do is to actually post it. Okay, you can write down if you want. Griffiths, maybe an author that you are familiar with, David Griffiths. I mean, of course, I don't want to be biased against any other books. This is the name and the book that came to my mind immediately. So that is a book that many of the students find a good one for undergraduate students find convenient. This one that you can consider as one of the. There are many books by David Griffiths. One is Elementary Particle Dynamics. That's one of the books that you can consider. Okay. Yeah. So other books, and there will be any other elementary particle books. Maybe I will give you some list of the books in the in the course announcement section. All right. So let me stop here, and we will meet next time. Yes, you can.